Nanoscience and Nanotechnology. Now, we know that every technology uses materials with specific properties. For example, the whole electronics depends upon the semiconducting property of certain materials which we call as semiconductors. Similarly, structural materials are there with the desired properties which are required for construction work or for making machinery, vehicles, etc. In short, in order to realize technology, we need materials with desired properties, or we are in quest of materials with tailor-made properties. In this context, nanomaterials become relevant. Now, why nanomaterials become relevant is due to the following reason. Nanomaterials are crystalline or amorphous solids, the size of which is of the order of a few nanometers, typically 1 to 100 nanometer, in at least one dimension. Now, these materials are relevant because almost all materials like metals, semiconductors, or insulators, almost all materials in the nano form exhibit physical and chemical properties which are drastically varied from those of corresponding bulk material. Now, in the context of nanomaterial, bulk material means a material with the same chemical composition but larger size. The size is of the order of maybe millimeters, maybe micrometers, or maybe even meters. Now, an example is band gap of a semiconductor is actually a characteristic of a given semiconductor. Now, at a given temperature that doesn't change. Maybe by doping we can slightly change the band gap. But when the semiconductor becomes a nanomaterial and below a critical size, the band gap changes without any change in chemical composition. Actually, the band gap increases gradually when the particle size decreases. Similarly, metals also show varied optical properties when the size becomes extremely small. Now, the word nano actually is derived from the Greek word for dwarf. Just as 10 raised to minus 2 is called centi, 10 raised to minus 3 milli, 10 raised to minus 6 micro, 10 raised to minus 9 stands for nano. Or 1 nanometer is 10 raised to minus 9 meter or 1 billionth of a meter. And nanomaterials have particle size 1 to 100 nanometer in at least one dimension. So this we have talked about the definition as well as the term nano. And now nanoscience and nanotechnology. Now these, as I said, the physical properties of nanomaterials are different from those of their bulk. So we have to explain it using theoretical explanation for these varied properties are to be given. And the science that explains the phenomena of physical properties of nanomaterials is called a nanoscience. A more formal definition is given in the box. That is, nanoscience is the study of phenomena and manipulation of materials at atomic, molecular, and macromolecular scales where properties differ significantly from those at a large scale. It deals with matter at the scale of 1 billionth of a meter. Now, nanotechnology means that you are using some structure or you have designed a structure or a device whose dimensions is of the order of a few nanometers. A formal definition means nanotechnologies are the design, characterization, production, and application of structures, devices, and systems by controlling size and shape at a nanometer scale. Now, the uh, chips that we have in our computer are actually examples of are actually nano devices. Now this slide actually shows certain things in different size scales so that the actual size of nanomaterials become clear. For example, see, the human cell is of the order of 100 micrometers. 1 micrometer can be read as 1000 nanometers. So it is 100,000 nanometers. Maybe bacteria is of the order of 5 micrometers. 5 micrometers actually means 5000 nanometers. Now, some bacteriophages, the size is of the order of 200 nanometers. Viruses maybe 100 to 800 nanometers, and we are talking about materials, the size of which is of the order of 1 to 100 nanometer. So we are talking about materials which are extremely small. But still remember that these materials are actually made up of atoms. So the size of the atoms is still smaller. It is of the order of a few angstroms only, and angstrom means zero point 0.1 nanometer. Maybe this the size scale of the nanomaterial is now clear to you. It's extremely small. We cannot actually imagine how small it is, but it is comparable to the size of the viruses and bacteriophages, maybe DNA and all. Now, just to see how much the properties change, maybe this is a very famous photograph of something called the Lycurgus cup. Lycurgus is actually a Greek mythology story character, and his story is engraved in this cup, and so that's why it's called a Lycurgus cup. Now, the two cups you see are the one and the same. It is made up of glass in which gold nanoparticles are embedded. Now, metals have a peculiar property that they absorb and reflect the same color, and if they are extremely thin, they could transmit the complementary color. Extremely thin, of the order of a few nanometers. Now, the cup on the left is seen from using white light from an outside source. So you are seeing the reflection. It's green in color. So the gold is actually absorbing and reflecting green color. Now, if you keep the white source inside, and maybe if the room is dark, then the cup will appear pink, because the golden nanoparticles will transmit the complementary color pink. So bulk gold will not do this. So this much of change in optical properties happens when the material becomes nano. Maybe again another visually you can see that all these things are silver. The only thing is the size is different. See, silver and gold. Say AG is actually silver and the AU is gold, and you can see that different colors you can see. Then these colors actually change with the particle size. See, when we see these colors, it is not only the color changes, but the other physical properties are also changing. Now, again, another example are the paintings in the uh, glasses of medieval churches, where gold and silver nanoparticles were used to make different colors, and these are actually the physical colors, not the chemical paints that we now use, but the physical colors of gold and silver nanoparticles very artistically used for these paintings. Just these slides actually shows that the physical properties of materials show drastic changes when they become nanomaterials. Of course, during these times, the size of the particles were never measured, but they knew some procedure to make gold with this color and silver with this color and so on. Now, in fact, a systematic study of nanomaterials started with a statement from Richard Feynman, the famous physicist, who made a statement that there is plenty of space at the bottom, by which he meant that if we have the power to manipulate things at an atomic scale in the nanometer range, then we can achieve new material properties hitherto unknown. So actually he was a theoretical physicist, and from theoretical considerations he predicted that if it is possible to control structures at an atomic scale, then new properties can be achieved. And this was actually the starting point of what you now call as nanoscience and nanotechnology. Now, the term nanotechnology was formally used in 1974 when Norio Taniguchi, a researcher in the University of Tokyo, Japan, used it is to refer to the ability to engineer materials precisely at the nanometer level. Now, in our syllabus, uh, we have to learn the following. That is why nanomaterials show properties which are different. We have to learn 2 points only. In fact, there are many points, but we have to learn only 2 points which are common for most of the nanomaterials, or rather general for most of the nanomaterials. And then there is something that called a quantum confinement. Then we have to learn about nanosheets, nanowires, quantum dots. Again, something on the optical, electrical, and mechanical properties of nanomaterials also has to be learned, and a few applications of nanotechnology. Now, this is Norio Taniguchi who coined the term nanotechnology. Now, why nanomaterials shows different properties compared to their bulk counterparts? There are mainly 2 points. One is increased surface to volume ratio, or more correctly, increased surface area to volume ratio, and two, the dominance of quantum size effects. Now, let us see what is meant by this large surface area to volume ratio. Now, you imagine a sphere. Now, need not be a nanoparticle, maybe you imagine a sphere with radius r. Then the volume is 4 by 3 pi r cube. Surface area is 4 pi r square. Now, the total number of atoms constituting this sphere is actually proportional to the volume. Or more correctly, volume is proportional to the total number of atoms in the sphere. Similarly, surface area is proportional to the total number of atoms on the surface. So if you want to find the fraction of atoms on the surface, then you have to find the ratio of total number of atoms on the surface to the total number of atoms in the sphere. That is, the fraction of atoms on the surface is equal to total number of atoms on the surface divided by the total number of atoms in the sphere. Now, the numerator is proportional to 4 pi r square and the denominator is proportional to 4 by 3 pi r cube. That leads to surface area to volume ratio equal to 4 pi r square by 4 by 3 pi r cube, that is equal to 3 by r. It means that when r decreases, surface area to volume ratio increases. Now this is true even for bulk material. So the more surface to volume ratio is there for a 1 millimeter sphere in comparison with a 1 centimeter sphere. Now the point is, even for a 1 micrometer sized sphere, the fraction of atoms on the surface is very small. It is much less than 0.01%. But when you come down to nano size range, maybe for a 50 nanometer size, something like 10% of atoms will be residing on the surface. And as the size goes down, maybe for 1 or 2 nanometer, almost 70 to 80% of atoms will be residing on the surface. Now, how this affects the material properties is due to the following reason. Now, you know about surface tension of liquids. Why surface tension occurs? Because we know that a molecule or an atom within the liquid is equally attracted in all the directions, so there is no attractive force. The forces cancels out, while if you consider a molecule on the surface, then they are attracted towards sideways as well as into the liquid, which means that a tension is created on the surface, and that is the origin of surface tension of liquids. Now the same thing is true for solids also, but it is not that evident since atoms in the solid cannot freely move. But still, the environment of atoms on the surface is entirely different from the environment of atoms in the interior. Now, for a bulk solid, the most of the physical properties are actually due to the atoms of the interior, as the fraction of atoms on the surface is negligibly small. But when you come down to nanomaterial range, the fraction of atoms residing at the surface becomes large, or even larger than the atoms of the atoms residing at the interior. This means that the physical properties are determined mostly by atoms on the surface. So this is one reason why nanomaterials show varied properties. Now, the same thing calculation you can do for a sphere also, for which you can refer to your textbook. There what they have done is they have found the total surface area of the cube, they have found the area of cross section of the atom, so they have found the number of atoms on the six faces, then the uh, volume of the cube as a cube and the volume of each atom as 4 by 3 pi r cube. Again you find the ratio and you will get the result that it is proportional to 1 by a. It is proportional to 1 by a means where a is the side of the cube. So for any three-dimensional shape this is true. When the size becomes small, the fraction of atoms on the surface becomes large. Now a calculation for iron is given, for which also you can refer to your textbook. So as the particle size decreases, greater proportion of the atoms are found at the surface compared to the inside. And atom on the surface in a different environment compared to atoms in the interior, or they are in a different potential compared to atoms in the interior, and that leads to varied properties of nanomaterials in comparison with their bulk counterparts. And this larger surface area to volume ratio is advantageously used in the area of catalysis. Actually, the catalytic action happens only at the surface of the catalyst. So if the catalyst is in the nanomaterial form, then with the same mass you can have more catalytic action, or the efficiency of the catalyst increases. Similarly, suppose you have a material that is emitting light. Now the light emission happens only from the surface. So if the emitter is in the nanomaterial form, you can have more emission from smaller quantity of material, again which means a better emission efficiency. So thus the large surface area to volume ratio of nanomaterials can be advantageously exploited in many areas such as catalysis, light emission, light absorption, and so on. Now, the second point that we have to learn why nanomaterials show varied properties is called the quantum confinement. Now, most of the physical properties of solids are due to the behavior of their electrons in the solids. For example, whether a material is a metal, is a conductor, semiconductor, or insulator depends upon the number of conduction electrons available at a given temperature. Now, let us think about these free electrons. Now, in a bulk solid, these conduction electrons are free to move about in all the three directions. But if the size becomes small in all the three dimensions, so that in all the three dimensions, suppose the size is below 100 nanometers, then we have the case of a particle in a box problem in a three-dimensional box. You have learned in your quantum mechanics class that when a particle is confined in a box, what will happen is that the particle cannot have any value of energy. A free particle can have any value of energy. A free electron in a metal can take any value of energy within the stipulated range. But if the electron is confined to nanometer range, what will happen is that it cannot take any value of energy. Rather, just like the particle in a, it is actually a particle in a box problem where the permitted energies become discrete. So the movement is actually confined. It can take certain values of energy only. And this happens when the de Broglie wavelength of the electron, again de Broglie wavelength you have learned, de Broglie wavelength and the dimension of the material are comparable. Only then this confinement occurs. And when that happens, the quantum effects that we have learned in our quantum mechanics dominate the behavior of the material at nanoscale, and this will affect the optical, electrical, and magnetic properties of the material. Now, based on the number of dimensions in which the confinement occurs, we can classify them into nanosheets, nanowires, and quantum dots. Now, nanosheets means the confinement is only in one direction. So it is something like a sheet where the two length and breadth are there, which is greater than 100 nanometer, but the thickness is less than 100 nanometers. So there is confinement, or the thickness is comparable to the de Broglie wavelength, which means that the confinement is there only in one direction. In the other two directions, the electron can move freely, but not in one direction. So this can be realized by a thin layer of a low bandgap semiconductor sandwiched between two layers of semiconductor with larger bandgap. So which means that that electron can freely move in two directions, but in the other direction, it has discrete energy levels, or it cannot take any value of energy. Now, the second confinement example is a nanowire. A nanowire means in x and y directions there is, or two directions, there are confinement, and the length is actually larger than 100 nanometer, or the de Broglie wavelength, and there is no confinement only in one direction. So the motion of electron in that direction is not restricted, but in the other two directions they are confined, and in those directions the energy levels exist. Now, quantum dot means in all the three directions there are confinement. It is something like a particle where in all the length, breadth, and height falls in the de Broglie range. So the electron is actually confined in all the three directions. So it becomes a three-dimensionally confined electron. So nanoparticles with the size of the order of maybe 1 nanometer to 10 nanometer can be treated as example of three-dimensionally confined material. Now this image actually makes it clear. This is a three-dimensional material. You have conduction band and valence band, whereas in the one-dimensional confined case, here there is confinement, but not in two directions. There, what will happen is that the band structure actually changes to something like this, something like step in one direction. And in the two-dimensionally confined case, in two dimensions, discreteness occurs, but in one direction, the free movement is possible. And in 3D confinement, in all, the energy levels become something similar to that of atoms. That is why these quantum dots are sometimes referred to as artificial atoms. Now these are the formulas for energy. Now you remember the for nanosheets when there is one-dimensional confinement. So this term is the one that we used in the particle in a box problem, where n can take values 1, 2, 3, etc. Mass of the particle, size is L along the z direction, while in x and y direction h cut square k square is actually p square, the momentum square. Momentum square by 2m is the kinetic energy. So these two terms are the kinetic energy terms for free particle in x direction and y direction, whereas in the z direction, it is discrete energy levels. For nano wire, there is confinement in two directions. Here it is y and z direction. Confinement is there, whereas in x direction, there is no confinement. It can move as a free particle. And in quantum dot, the confinement occurs in all the three dimensions, x, y, and z, and discrete energy levels exist as far as three directions are concerned. Now, the wave functions of electrons in for nanosheets, nanowires, and quantum dots are also given. Here, in the z direction, the particle in a box term is there, whereas for x and y, it is a free particle. Here again, in the y and z direction, the particle in a box term is there, and in the x direction, it is a free particle. And for the quantum dot, all the terms are the discrete terms. Now, one example of this quantum size effect is in the case of semiconductors, where the band gap widens when the material becomes a nano material. So that can actually be explained with this diagram. This is the diagram that you have learned in probably in your plus two, which classifies or which classifies solids into insulators, semiconductors, and metals. In the case of insulators, the band gap is greater than 6 electron volt. Semiconductors, it is 1 to 2 electron volt. In the case of metals, there is no band gap at all. So for insulators, the absorption will be in the ultraviolet region of the spectrum, because these photons have very high energy, whereas visible photon has energy of the order of 1 to 2 electron volt. So that is our semiconductor has a band gap of the order of 1 to 2 electron volt, which absorbs in the visible region of the spectrum. Now, let us suppose for our discussion, we will discuss the case of a hypothetical semiconductor where the absorption is in the yellow region of the spectrum. Now, when the semiconductor becomes a nano semiconductor, what will happen is that the band structure is not complete and the band gap actually widens due to quantum size effect. And due to this widening of band gap, now the material will be absorbing higher energy photon probably towards the blue region of the spectrum, and this is called the blue shift. And again, if the same material without any chemical change becomes still smaller, the band gap could still increase and become violet. So there is actually a variation from towards the blue region of the spectrum when the particle size becomes smaller, and this is called the blue shift in the case of semiconductors, and this is one of the examples of quantum size effect. Now, this can be used in the case of tunable lasers. For example, there are semiconductor materials that can be used for lasing, but the number is limited. So, if you can change the band gap of that material by changing the particle size, then what we can achieve is that lasers with different colors can be produced. This is again a slide that shows the quantum size effect, which we already discussed. And again, another slide that shows how a bulk semiconductor, the band gap increases when the particle size becomes smaller and smaller in the case of three-dimensional confinement. Now you could see the difference. Actually, these are fluorescing materials. So these materials, semiconductor materials, giving out color, giving out light. How it emits light is by maybe by excitation. The electrons go to the conduction band, and when they return to the valence band, the color is emitted. So the color emitted is actually a measure of the band gap. So larger size means it will be red in color. The same material, when the band gap increases, it becomes yellow, green, maybe, and finally it becomes blue, which means higher band gap. Now, the blue shift in the case of semiconductors we have discussed. Now, another optical property that is relevant or that is important in the case of nanomaterials is the surface plasmon resonance in the case of metals. Now, we know that different metals have different colors. Gold has a particular color, silver has another color, copper has another color, and so on. Now, these colors are actually due to surface plasmon resonance. Now, these metals have large number of free electrons in them, and these free electrons act collectively. They actually have a definite frequency. They actually oscillate with a definite frequency, and but that particular metal will absorb and reflect that color, that particular frequency, and that leads to the color of that metal. Now, when the material becomes very small, when the metal becomes very, very small, what will happen is that the plasmon frequency will actually increase. Now, the plasmon frequency increase means that the color that the metal absorbs and reflects also changes. That is what we have seen in the earlier slides, where the gold and silver shows different colors with change in particle size. This phenomena is called the surface plasmon resonance. And this can take place only when the size of the nanoparticle is smaller than the wavelength of the incident radiation. So they naturally happen at a very small size. Now, electrical properties of materials also show change when they become nanomaterials. Now, sometimes the electrical conductivity decreases with the reduced dimension due to the increased surface scattering and change of electronic structure. Now, surface scattering means the following thing. Now, suppose you have a crystal. Now, the grain boundary of a crystal is something like a uh, a potential wall. So it is a crystal defect actually. And when and conductor electrons is actually scattered at this grain boundary, and as the particle becomes smaller and smaller, the number of grain boundaries becomes more and more, and due to the scattering, the electrical conductivity could decrease. Another thing is that in the case of a nanomaterial, the continuous energy bands may be replaced by discrete energy levels when the particle size is extremely small, and this could also lead to band gap increase as the size decreases. This could also decrease the electrical conductivity. Sometimes these nanometals could even undergo transition to semiconductors or even insulators at extremely small sizes, and this happen only when the particle size becomes extremely small. Now, another thing with regard to the electrical property is that when there is something called a mean free path for electrons. So mean free path means the distance an electron can move without scattering or without colliding with another electron. Now, if the size of the material, then that length is actually of the order of a few nanometers. So if the size of the material is less than that length, then the electron can actually move very fast without any scattering. This is called ballistic conduction. In fact, ballistic conduction occurs in the case of what you call as the single electron transistors. They are actually semiconductor devices which are extremely small, where the size of the device is smaller than the mean free path of electrons. So this actually enhances the electrical conductivity. Again, sometimes the electrical conductivity can be increased due to better ordering of the microstructure. It means that there are crystal defects which act as scattering centers for free charges. In the case of nanomaterials, there is something called a self-purification effect, due to which all the crystal defects, such as vacancies, will be residing at the surface. So the interior of the nanomaterial will be free of defects. So in the interior, the electrical conduction can happen in better compared to a bulk crystal. So there are situations where the electrical conductivity decreases, as in the case of a metal, or due to the presence of a larger number of grain boundaries. And there are cases such as ballistic conduction occurs in the case of semiconductors, and there are cases in which the electrical conductivity is enhanced due to better microstructure, due to the decreased concentration of defects.